We're going to go over section 711, Aufbau principle. We're going to do electron configurations and orbital diagrams. So first you need to remember that the first two columns of the periodic table would represent s electrons. These elements are not s electrons. Don't confuse that. It's just how we fill the orbital diagrams or how we write electron configurations. You think of the first two columns being s electrons, the last six columns being p electrons. Now careful, the little box right here is an s electron, not a p electron. And in the middle, we will have our d electrons. So we have our s, our p, our d, and those bottom two rows of the periodic table, those represent our f electrons. So let's do the electron configuration for germanium. So germanium would land right here on the periodic table. And we just go left to right, up to down. So we go left to right, fill up the first row. So we have 1s, 2 boxes. And then we go to the second row, 2s, 2 boxes. We're in the 2p's now. And there were 6 boxes, 3s. There were 2 boxes, 3p, 6, 4s, 2, and careful with the D's, they're one less than the row number that you're in, 3D10, and then we're up to 4P and 2. Okay, there is the shorthand configuration. We look for the noble gas one row above the element. So over here we have argon. It's one row above germanium, the noble gas. We will write argon. And then we still have to include all the electrons in the same row up to and including the element. So now we're going to start here. We still have 4s2. Then we have our 3d10 and our 4p2. That would be the shorthand configuration. So now let's look at our orbital diagram. To figure out how to set up your orbital diagram, first you need to have energy on the y-axis. There's no label for the x-axis. And we still go left to right, top to bottom, up to and including the element to figure out where we are going to go with our electrons. Okay, so we're still doing germanium. We're going to do this for germanium. And we look at our periodic table. First thing we would hit is a 1s. So we'll write a 1s. And the next thing we would hit is a 2s. And going to continue to the right. Then we would hit a 2p. I'm putting the 2p's over to the right on the orbital diagram. You don't have to do this. You could line everything up on the left, but I like to keep the p's lined up and the s's lined up. Next thing I hit is a 3s. And we keep going higher and higher. The energy gets higher and higher as you go left to right, top to bottom on the periodic table. Next is a 3p. Then we have a 4s, a little bit higher, the 3ds, and lastly we hit some 4p's. And we're going to run out of space here. Okay, move things around a little bit to make more sense. We stop at the 4p's because germanium, we hit germanium in the 4p's. Now, 1s's you should recognize or remember, they all have only one orbital. So we'll put a little line here representing one orbital. So each s we will put a dash. The dash represents the orbital. P's, hopefully you remember there are 3 orbitals for a p sublevel. Here we go. And D's, how many orbitals in a d sublevel? It's 5. Okay, so germanium is element number 32. So there's 32 protons, 32 electrons. We're going to start filling. We fill bottom to top. And we fill a row before we move up. Fill a row before moving up. Okay, fill a row before moving up. That is Aufbau. Aufbau's principle. You say, oof, I'm full. So Aufbau, fill a row before moving up. And we also have Hund's rule, which says, put 1 electron per orbital in a sublevel before pairing electrons. So we have our 32 electrons we need to put in here. And let's start. We start at the bottom. 1, 2. Remember, there can be 2 electrons per orbital. I've filled that, I can move up. 3, 4. I have filled that, I can move up. That was Aufbau's principle. Now, 5, 6, 7. Notice I filled 1 per orbital before pairing up. That was Hund's rule right there. 8, 9, 10, 11, 12. Watch, you can do this. 13, 14. That's okay. 15. They all have to point in the same direction before you start pairing them up. So when you put 1 electron per orbital, make sure they're all pointing in the same direction. That means they have the same spin, magnetic spin. So where were we? 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, and I stop. Notice on that 4p I made them both point downward. They could both point up, they could both point down. They could be in the first and the third, first and second. They just have to be in 2 different orbitals. And they have to point in the same direction in this last orbital. Now if I asked you a question, how many unpaired electrons? How many unpaired electrons does germanium have? If you look at this, hopefully you see everything is paired except in the last sublevel. Everything has to be paired except the last sublevel based on Aufbau's principle, because you have to fill a row before moving up. Well, if that's true, everything's filled except for the very last sublevel. So how many unpaired electrons does germanium have? 2, right here. 2. Okay, let's do a couple more problems. I'm going to do how many unpaired electrons does each of the following have? Okay, so let's do cobalt. And let's go back to our periodic table. I'm going to erase everything that's in here. Cobalt is right here. Here's cobalt. Now, I don't have to check anything up until this D sublevel right here, because everything other than that last sublevel is going to be paired up. So I'm going to check the 3Ds. So 3D, and a 3D has 5 orbitals. And let's count how many electrons are going in there. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to put 8 electrons in there. 1, 2, 3, 4, 5, 6, 7, 8. And I see there are 2 unpaired electrons. Okay. Let's do niobium, NB. Niobium. Niobium is number 41. It falls right here. Niobium. So which sublevel do I have to check? Hopefully you got it. We're going to check the 4Ds, and note we have 1, 2, 3 electrons in the 4Ds. So we'll do 4D, 1, 2, 3, 4. There's 5 orbitals, and we need 3 electrons. 1, 2, 3. I have 3 unpaired electrons. You might wonder, why do we care about these unpaired electrons? Well, there's some definitions in here. And here are 2 new definitions. We have paramagnetism. That's where you have a slight magnetic attraction of an element, and you have at least 1 unpaired electron that causes the paramagnetism. There's something also called diamagnetic or diamagnetism. If something is diamagnetic or diamagnetism, there's no magnetic attraction and the substance has no unpaired electrons. So let's look back at our two examples. Is cobalt paramagnetic or diamagnetic? Well, it has two unpaired electrons, so this would be paramagnetic. Paramagnetic. And niobium, oh, it's got three unpaired electrons. It is also paramagnetic. In fact, unless you're at the very end of a sublevel, you're going to be paramagnetic. So for instance, all the elements that fall in these blocks right here would be diamagnetic. All the elements that fall in right here would be diamagnetic, and all the elements that fall right here would be diamagnetic. Because their sublevels would be all completely filled, whatever sublevels they had. There'd be no unpaired electrons, and they'd be diamagnetic. Everything else should be paramagnetic. That kind of simplifies it, doesn't it? Okay, so we have some exceptions to Aufbau's principle. Copper and chromium. So copper, turns out the configuration for copper is argon. We're going to do the shorthand. Argon 4s1 3d10. What happened here, we would have expected to have 4s2 3d9. We would expect 4s2 3d9. But one of the s electrons jumps to the d sublevel, and this is actually lower energy. So the electron configurations, we want to create the lowest possible energy configuration. Turns out this is a lower configuration than this. Now, your book says scientists, chemists are still disagreeing why this happens. I used to explain it a certain way. I'm not going to explain it that way anymore because your book is saying that people don't agree. So I don't want to tell you something that people are now currently disagreeing about. You just need to know copper is not what we would expect. It's not. Chromium is also argon, shorthand, 4s1 3d5. So we would have expected it to have a 4s2 3d4. Once again, one of the s's has jumped to a d orbital. So these are two of the exceptions in the 3d, elements that fall in the 3d block. Let's go back and take a peek. So right when we're at the 4th and the 9th spot. And this also happens in the 5th shell, or the 4D elements. In the 4D block we have those exceptions, in the 3D block we have those exceptions. But then the exceptions don't happen exactly the same in 5D. So we can't make any generalizations, you just need to know about the ones in the 3D block for certain. One other thing I haven't talked about is these F electrons. I won't ever give you a problem where we're falling within the F or the 4F or the 5F sublevel, because the configurations don't really work according to Aufbau and Hund. It's just they get a little messed up. But I could give you something that falls beyond. So for example, lead. What you need to know about the Fs, wait, that's not lead. Lead is in the 6th row. Yep, that is lead. This is Pb right here. Pb. If we're going all the way to the 6th row, I'm going to do a quick shorthand configuration for lead. So let's see, what's above lead? We have xenon. Xenon, 6s2. Now, we're going to have to go, notice it looks like it's 5d1, and then 4f14, and then 5d9. But we're going to put all those d's together. Okay, so we had the 5d1 and the 5d9. We're going to put those all together. So we're going to go, and we also have to go all the way through the 4f. So we'll go 4f14, 5d10, there were 10 total here, and then 6p2. And that's the configuration for lead. So you'll notice these little arrows. If you look at the atomic numbers, you'll notice we skip when we go from lanthanum to hafnium, all of a sudden we go from number 57 to 72. It's like there's something's missing. Well, those are all right here. The reason we don't show those in here is because the periodic table would not fit on a single piece of paper. Okay, now we're going to talk about valence and core electrons. Hopefully you remember your valence are your S and P electrons in the row of the element. Only your S's and P's. Valence means outer, your outermost electrons. Do you remember why D's can never be in the outer shell? If we look back, D, 3D, 4S. In order to get to a 3D, you had to get through the 4S first. D's are always one less than the row that they're in. If you look at the rows and you look at the D's, D's are never your outer electrons because they're always going into an inner core shell, sublevel. So your valence electrons are only your S and your P electrons. Your core electrons are all the non-outer electrons, all the non-valence electrons. We call those the inner core. It's like an apple core. If you think about what's on the inside, it's your core. What's on the outside is your valence. So let's do some valence electron problems. Let's find the valence electrons. Okay, let's do valence electrons for bromine, phosphorus, and rubidium. You really need your periodic table here. Bromine's in the 4th shell. It's number 35. And it would have 4s2, 4p5. Phosphorus lands in the 3rd shell. It's number 15. And hopefully you can do this along with me. We would have 3s2, 3p3. You can pause if you want and do these on your own. I should have said that earlier. Rubidium is in the 5th row. It's just a 5s1. Okay, those are our valence electrons. So the core electrons for each of these would be all the electrons that are not these electrons. Okay? I won't ask you for the core electron configuration, but you need to know what the core electrons represent. Okay, now we're going to talk about the electron configurations for ions. Don't forget, if you're a negative ion, you need to add electrons. If you're a positive ion, you take away electrons. So let's find sulfur. Sulfur is number 16. So find number 16. And we're going to do these shorthand configurations here to make life easy on us. So S2 minus, we add 2 electrons. Notice we end up with the same number of electrons as argon. We would have 18 electrons. And the shorthand configuration is argon. Okay? Chlorine, 1 minus, chloride ion. Chlorine is number 17. We add 1 electron, and we end up with 18 electrons, and the shorthand configuration is argon. Ca2 plus. Okay. Ca is number 20. We're going to take away 2 electrons. Becomes 18 electrons, and the shorthand configuration is argon. All right. Rubidium, 1 plus. Rubidium is in the 5th row, and it's number 37. We're taking away 1 electron to have 36 electrons. And this would be, shorthand would be krypton. Now, do you notice that S2 minus, Cl1 minus, and Ca2 plus all have the same configuration? Did you see that? They all have the configuration for argon. That's called isoelectronic. Isoelectronic means same electron configuration. Okay. Okay, I just decided I'm going to move periodic trends into a separate video, so it'll be another video to see.